At this point, you know how to express the chemical formulas that make up real-world substances using symbols from the periodic table, subscript numbers to indicate how many atoms of a substance there are, and then coefficients that show how many molecules of an entire substance, crystal units of a substance, or atoms of a metal substance, how many of those things you have. You know the purpose of coefficients, of subscripts, and of chemical symbols. But right now, just knowing how to write chemical formulas, it has limited usefulness because all you can do is express what substances are. You haven't yet developed the ability to predict what's going to happen during chemical changes. Well, that's what this lesson's all about. We're going to, in this lesson, practice doing something with chemical formulas that chemists do all the time. We're going to practice balancing a basic chemical equation to give you some practice with what chemical formulas are used for, what they are all about, predicting the numbers of crystal units, molecules, or atoms that are going to react in a chemical reaction to produce a certain product and being able to predict how many atoms, molecules, and crystal units there are in the product. Let's get started balancing a chemical reaction. And as we get started doing this, we're going to take a look at the rule that guides everything that we do when balancing chemical equations. That rule is the law of conservation of mass, which states that we cannot, when we balance chemical equations, we cannot have more atoms after the reaction than we have at the beginning of the reaction. Any atoms that are available that are present at the beginning also have to be present at the end. And any atoms at the end had to have come from somewhere. They have to be there at the beginning. So we need to make sure that the atoms in the reactants are the same as the atoms in the products. However, the bonds between atoms and the arrangement is going to change. Our example that we're going to look at is potassium nitrate decomposing and turning into potassium nitrite and oxygen. Potassium nitrate is a white powdery substance pictured on the screen, and it is used in the making of slow-burning fuses. Now, here's why it's used for that. Usually, slow-burning fuses use a combustible substance, sometimes even things like sugar, to sustain a chemical reaction as they burn. But sugar actually burns very, very quickly, and usually it'll burn out very, very quickly because it produces waste products too fast and uses oxygen too fast. So when you add a substance like potassium nitrate, take a look at the chemical equation on the screen. Do you see that potassium nitrate makes more oxygen? So as you heat up this potassium nitrate, it's actually going to produce extra oxygen that can be consumed during the chemical reaction so that as the sugar burns up on the fuse, more oxygen is present and it keeps the burning reaction going. But right now, as this chemical equation is written, there are not the same number of atoms on the left as there are on the right. Let's take a look at how we can fix the reactants and products of this chemical reaction equation. First off, let's make potassium nitrate, KNO3. Now just notice there's only a subscript after the O, which means I have one potassium, one nitrogen, and 3 oxygens. Let's see what that looks like. Here's my 1 potassium, 1 nitrogen, and 3 oxygens. Now this is how I would expect that you will probably make most of the substances that show up in chemical reactions. You will just connect the atoms together by having them touch each other to show that this is one molecule of potassium nitrate. It's not separate things. If it was potassium separate from nitrate, NO3, the equation would have a plus sign between them. Because there's no plus sign, because it's just KNO3 altogether, it must be one molecule of KNO3. However, as a science teacher, I realized that this picture that I made isn't 100% accurate because potassium nitrate is actually an ionic substance which makes crystals. So when I make these and I show you what these look like in pictures, I'm always going to make them the correct way. you can feel free to make potassium nitrate as a molecule like this if you want. The correct way that I'm going to do it is I'm going to show the crystal lattice in the background and how the potassium is one ion and the nitrate actually makes another ion, and they attract each other and stick together with the lattice. All right, so we've got potassium nitrate. Now, here's what you do first when you balance chemical reactions. Anything that's on the left side, the reactant side, also has to be on the products side. So you're going to make a copy of everything you put on the reactant side, and you're going to move it over to the product side. But when you move it, the chemical reaction that happens breaks apart all of the bonds. So this is how it's going to look. All of the bonds have been broken apart. So I've just taken what was on my reactant side and moved it over to the product side so I can make the substances over there. Now, I have to recombine and rebond these together to make the two substances on the products side of the reaction. Now, notice over there I have KNO2, potassium nitrite, and O2, oxygen. This is how they're going to combine together. I have to make KNO2, that's going to be another crystal, and if you wanted to, you could just combine them all together as one molecule if you like. And then I have to make O2, but hold the phone, I only have one oxygen. I can't make O2 with the pieces that I have here. So am I done? Not yet. I'm only done when I have the things that are stated in the chemical reaction equation. I'm only done when I have potassium nitrate on the left, on the reactant side, and potassium nitrite and oxygen molecules on the product side. So if I can't make a full oxygen molecule, I need to do something else to make this work. Here's what I can do. I can make another reactant. I'm going to add another potassium nitrate on the reactant side, and I'm going to copy it and move it over to the product side because I have to have those same exact atoms on the reactant side and the product side. And I'm going to recombine things to make what's on the product side. Here I'm going to have a potassium nitrite crystal and an O2 molecule, and now I can make my O2. Now I only have potassium nitrate, potassium nitrite, and oxygen. I am done because I have the things that are stated in the chemical equation. I'm just going to clean things up a little bit. These two crystals that are pictured don't look like crystals actually do, so I'm going to make them look like actual potassium nitrate and potassium nitrite crystals. And then I'm going to add in my coefficients into my equation. Let's count up. How many crystal units do I have of potassium nitrate? It's not just one, there are two of them, so I need to put that in my chemical reaction equation at the top. The same with potassium nitrite. There's not just one potassium nitrite unit, there's two of them. And for oxygen, O2, I only have one molecule, so I do not put a coefficient for that. I don't need it. Now we have balanced this chemical equation. Just one more thing I want to emphasize. Feel free to make everything, instead of as crystals, as molecules, if you're more comfortable with that. It's much easier to do, and I actually highly recommend that you do it that way because it will help you to keep things straight. This is what it would look like if I made things as molecules. I could have arranged them any way I wanted to. This is how I chose to arrange them and make them look. These are the substances that are available at the beginning and that are formed during this chemical reaction. All right, one last thing to do. I noticed that I have two potassium atoms on the reactant side, and there are two potassium atoms on the product side as well, so potassium balances. I noticed that I have two nitrogen atoms on the reactant side, and there's two nitrogen atoms on the product side, so nitrogen balances. Finally, I have 6 oxygen atoms on the reactant side and 6 oxygen atoms on the product side. Everything balances. This is a correctly balanced chemical reaction equation. So this is how you balance simple chemical reaction equations. Make the substances on the reactant side, copy them, and move the copy over to the product side because you have to have the same atoms on one side as on the other, and then rearrange them like happens in the real chemical reaction to make only the substances that are products. And at the end, don't forget to add in those coefficients at the top to make the equation correct.